Let's hand it off to you, Daniel, to maybe to kick things off. Just as a preface, really the spirit of these events is, finding intersections and points of tangency between different categories or disciplines in deep tech. And today, really, the focus is around zero knowledge proofs, which has taken the crypto world by storm, and machine learning, which has taken the rest of the world by storm. And we're going to essentially fuse those two topics together. So I think Daniel is probably one of the foremost experts on this subject. He's humble, so maybe he wouldn't say that himself. But tell us a little bit about kind of how you got into the space, what exactly zero knowledge proofs are, and why it's important in this advent of increasingly powerful and accessible artificial intelligence and machine learning. Why is it important to hold these tools accountable through zero knowledge cryptography?
Yeah, for sure. Yeah, and I was mentioning this earlier. I don't have any slides, so I'll just speak from the heart. The story of zkML, at least from the modulus worldview, obviously starts with the modulus story, and our story starts with very simple, an experiment. At that point, when we first started the company, we had just decided to not pursue our PhDs at Stanford and instead spend our time messing around with all this crypto stuff that's happening. Had zero skills in terms of discerning signal from noise by looking at Twitter, but we could read papers. And so we read every paper that we could possibly get our hands on. And very quickly, all the academic work, as well as the applications around zero knowledge cryptography, really kind of spoke to us both as kind of math nerds, as well as just kind of folks who were looking for kind of that inflection, right, where that technology was getting much better, much faster. And it was so clear to us that ZK was kind of where that action was happening. And so at this point, we really only knew AI from our academic training and ZK from the papers we were reading. So back to that experiment, we thought, how hard would it be to actually encode a machine learning algorithm, even a simple one, in a zero knowledge circuit, right? This is something that no one had really done at the application level before. And so that kind of led to us stumbling into what became the world's first on-chain AI project. A very silly project. It was a little trading bot, 70,000 parameters, just trying to guess at whether ETH prices would go up or down tomorrow. But what was cool, of course, and this is really the kind of the thread that connects all of zkML, is it fully committed to this paradigm of tamper-resistant autonomous execution that is provided by this like blockchain network system. And so even though we told people, as an illustration of that feature set, to not put money into this non-performant trading bot, which didn't even have a call function, so like Modulus team couldn't even bring the money out afterwards. Folks on the internet just started sending dollars to keep Rocky alive, and the bot ended up trading for over a month, right, before it lost all its money, which makes sense because it's a very small model. We did not crack the crypto markets, but it was the seed of this idea, obviously, of what we now know as zkML. But for us, more specifically around, okay, if we could do kind of something interesting here with a very small model, what would happen if we brought really performant models on chain, much larger ones, the ones that are getting all the headlines, the Stable Diffusions of the world, the ChatGPTs of the world. That was about 8 months ago. Since then, we've been on this journey of trying to figure out exactly what are the technical unlocks we need to bring models on chain. And obviously, there's a lot to get into in that journey and all the projects we've done so far, as well as our overall technical worldview. But before we dive into that, which I think will be the protein of this conversation, maybe just a quick refresher on what zkML is specifically, at least kind of our definitions for it, so we can establish some common language, and then we can obviously always challenge the boundaries a little bit. The way I like to think about it is to break it apart, right? We'll start with ZK, the first two consonants. They're just very exciting letters, I know, but at least with zero knowledge cryptography, and this is probably folks already have some degree of knowledge in this. It was actually a tech invented back in the 80s as a privacy or a compute integrity technique. It's the ability to effectively convince a counterparty that you had done some math correctly without revealing anything about the underlying math, right? And kind of the canonical example that people like is like a Where's Waldo puzzle, where I want to know that Kyle figured out where Waldo was, but Kyle doesn't want to show me where Waldo is. And so potentially what you could do is cut out Waldo's head. It's very graphic from the puzzle. Show me Waldo's head. And I'm fully convinced that Kyle could not have possibly found Waldo if not for the fact that he's literally holding his head. But I don't know where Waldo might be. It's kind of silly, but what's of course really odd is that there's this corollary property of zero knowledge cryptography known as succinctness. And it kind of shows up a little bit in that previous analogy where if you think about it, it's really easy for me to check that Kyle was holding Waldo's head. It's actually much easier to do that than to actually find Waldo or watch Kyle find Waldo. And so, 30 plus years after the invention of ZK as kind of an academic technique in the realm of security, blockchain networks turns out to be an excellent application of this technology because compute is really expensive on blockchain networks. And of course, it's very easy to instead do the compute off the chain, but then use the zero knowledge cryptography process to prove the correct execution of that off-chain compute, thereby only rendering the kind of on-chain responsibility to the verification, right? You can also think of like a Sudoku puzzle, which is very easy to check, but much harder to actually solve. So this kind of combination of compute integrity as well as succinctness has formed kind of the foundational paradigm or the foundational building blocks of today's kind of blockchain-based context for ZK. And of course, there's also a privacy property, but we can dive into that maybe in the meat of the conversation, because it's actually underutilized, I think, in the blockchain context. But nonetheless, that's ZK, and obviously a lot to unpack there. The second set of letters is ML, machine learning, right? This is the process, and obviously everyone kind of has at least a visceral, I'm sure, exposure to this, but of exposing an algorithm to a ton of data, oftentimes labeled, sometimes not, so that the algorithm can actually pick up the capacity to semantically differentiate and classify new data, right? This is kind of like a robot approximating human behaviors and human decision-making, which is just conceptually totally wild, right? It's like this super expressive technology. And of course, Ran mentioned that he did his PhD, I think in like 2007 or something. Right after Ran wrapped that up, GPUs became available, which brought in the modern paradigm of deep learning. Turns out if you throw even more compute at that like process of algorithmic learning, there are just like emergent performant properties. And of course, we're continuing to go down that trajectory. And now we're stumbling into LLMs as the next big architectural milestone. But from vision networks to classifiers to natural language models, there's a ton of really exciting ML work that really has never been applied to the blockchain because of that kind of compute resource limitation, right? So that's machine learning. And of course, again, a lot to unpack there. As you can imagine, I kind of tease this up a little bit. The marriage for Modulus and for all the folks, I guess, excited about zkML is specifically around leveraging the ability for zero knowledge cryptography to bring really expensive compute, effectively compress it, and then elevate it up to the security standards of the chain so that you can integrate it into your smart contract and bring that exactly that kind of behavior set to the machine learning operation, right, or that process, thereby bringing AI up to the security standards of whatever smart contract you're integrating that into. So that is a super, super succinct crash course into zkML. There are a ton of ways of kind of reorienting those two topics and what are the intersections. But I think the last thing I'll say, and this is the end of my tirade, I promise, is the analogy that I like, right? And if there are any AI practitioners in the crowd, y'all would probably hate me for this, for kind of simplifying things. But nonetheless, this is how I like to think about it. I like to think of a machine learning algorithm kind of like a factory, right? So you can imagine like the architecture of the algorithm is like the different machines in the factory. The parameters or weights of the algorithm might be the settings on the machines, right? So like the knobs and the levers and where they're set and so forth. And during the training process of a machine learning algorithm, it's as though you're shifting machines around and tuning the levers and turning the knobs until everything is just perfect. You pass in oak and you get out on the other side of the factory, an oak door. You pass in, I don't know what other kinds of wood, mahogany, and you get out a mahogany door, right? The machine is perfect. The factory is great now. What ZK then, in the context of zkML, is imagine coming up to the factory and just dropping a giant cage on top of that factory, right? So everything is frozen, right? Oh, and by the way, you pull out the operator. That's really key. So the operator can't go into the factory and change any of the dials or bypass some machines or just feed in, their own blueprints. The machine itself is now kind of static. It's frozen in time, almost like a smart contract. All it can do is continue to take in oak and put out oak doors, take in mahogany and put out mahogany doors. And the operator is kind of like banging on the cage, desperate to get in. And we go, no, you cannot get in because of the power and the bronze of mathematics. Anyway, so that's zkML according to Daniel. Please don't tell anyone else about this analogy. It's highly IP protected. I take royalty every time you mention it. But yeah, that was Crash Course, Kyle. Please.
Yeah,